16 because the vector field was what? Conservative. If the vector field was wasn't conservative, you would likely get different answers. Cool, that was all. Great job. Hey, you got this section down. There's something else I wanted to show you from this section though. I'm only doing 2-dimensional vector fields. Does this work with 3-dimensional vector fields? It does. Except we just got to check a few more things. Okay? So, I'm going to use the first one on the sheet. What was the vector field on number 1? There you go. So before we get into green stem, I just thought, can we explore 3-dimensional vector fields? So what was the first one? I got an f equals zyx. Is this conservative? Question mark. Is this vector field conservative? That's what I want to explore. Okay. Well, I'm going to use my method I was doing earlier. For this to be conservative, that would mean this would have to equal what? Now that, right? But I don't know if that's true yet, so I still have to put my what? Question mark. I have to put the question mark. I don't know if this is true or not. So, question mark, maybe this is possibly an fx. And this is an fy, and possibly this is an f now what? Z to some function of x, y, z. I don't know, here I'm going to put it right here, I don't know if this exists. I'm going to put a question mark here. I don't know if that function of x, y, and z exists. Now before it was easier, I just did this what? fxy equals fyx. This is almost as easy, but we just got to check a couple pairs. Like what's one thing I have to check? I'd have to check what? fxy would have to equal fyx. You have to check that. But you're going to notice you got 3 more checks. What else would you have to check?
fx.
Get that pair. What's another pair?
fyz.
fyz would have to equal
fxy.
fzy.
zy.
And there's one more check. It's okay. This takes 3 times as long as the last problem. So what? It won't take that long. And what's the other pair I'm looking at? fxz, second derivative, right? These are second partial derivatives, would have to equal fzx. But I'm telling you, you and I check all 3 of these, and they all come out as check, check, check. That vector field is conservative. We can do line integrals in an easy way by using the fundamental integral line. And then we can say, oh, those line integrals are independent of path. All right, so let's see. Oh, and if you want, I should write this like the author too, because this gets a little sloppy. The author calls this what? P and Q and R. We're really just checking, does dP dy equal dq dx? Does dP dz equal dry? And lastly, what would this be? Does fxz dp dz equal the dr dx? Well, let's go see. What's the derivative of that with respect to y?
zy.
Wouldn't it be 0? Didn't have a y in it. Do you agree?
Oh yeah.
Cool. What's the derivative of that with respect to x?
0.
Hey, we're 1 for 1. Come over here. We're 1 for 1. That's true, right? What's the derivative of this right here with respect to a z? 0. What's the derivative of the z component right here, the z component, with respect to a y? Hey, 2 for 2. Well, if 2 work, another one doesn't, it's not conservative. We got to make sure this is conservative. Is fxz to an fzx. So what's the derivative of that? Aha, with respect to a z. 1. Sound agree? And what's the derivative of this component right there with respect to an x? Is this vector field conservative?
No.
Yes, it is. Yes, it is. Yes. Woohoo! It is.
Oh, they've all 3 of them don't have to be 0. They've all.
No, they do, very good question. They don't all have to come out as 0. They just have to come out as equivalent.
Oh, okay.
Now, this is a lot of funny sloppy writing, isn't it? But I want to tell you, you might prefer to do this, because this is what we cover tomorrow. This is really a preview to what we're doing tomorrow. They just use something called a curl vector to do this. That's all we got to check. Now, can you help me find that potential function there? What's the method? Integrate that with what letter? With respect to a x, put a plus. Integrate that with respect to a y, put a plus. Integrate that with respect to a z, and put a plus k. If you get any repeats, toss them. Let's try it. Let's integral that with respect to x.
Zx.
All right. And I'll write it in alphabetical order just to stay organized. We know this exists, so I can get this question mark on. This exists. You exist. We know it. We just proved it. It exists. Plus, let's integral that with respect to a y.
Y square over 2.
Good job. Now let's integral that with respect to a z.
Xz.
Now look it over carefully in case you write an answer like this on the
There
test.
will repeat.
Be looking out if you got any repeats. Do I have one?
Yes.
So you keep the original and just toss this one. But don't toss that, that was different, right? And can you check this? So when we check the derivative of this, we should get the derivative of all this with respect to x should be that. And the derivative of all this with respect to y should be that. And the derivative of all this with respect to z should be that. And then could you evaluate the line integral? Oh yeah, just do f of what? 1 point bar image? Cool. Awesome. Now, everyone's okay with all that? Nice. Now here's my question. Is the line integral going to be the same value for different paths from one endpoint to another endpoint? Will it always be the same in that vector field? Yes. Just like that example I had up there. Because the vector field's what? And sorry, does not matter on the path, it's independent of that. So the line integral, in other words, the way I wrote this, is the line integral going to give the same value for all different paths that we take? Yes. So we're saying this line integral is independent of paths. So I just want to point that out. There you go. It's independent of the path. When I'm talking about the path, the curve C. It doesn't matter, does not matter what curve you take. Whee. Hey, number 2, what did I have there? F of x, y, z equals negative y, x. All right. And would you check that? Is that vector field conservative? Is this vector field conservative? I'll get that out of the way. I don't know if I can write that. How about this one? Negative y, xz. And then when I'm done, when I ask you, is this line integral independent of that? Is that vector field conservative? What's sort of that? There's maybe an fx, maybe that's an fy, maybe that's an fz. But I'll put question marks. I don't know if these exist. Because I don't know if fxy, function of x, y, and z exists. What's the partial of that with respect to y? Okay. What's the partial of this with respect to x? We already know the answer. That's enough. What do y'all think? Is f conservative?
No.
No. That's all done. That's all it takes. So you go. Because I don't even have to check these. Here, I'm not even going to check these. It's already over. It's over. This vector field's not conservative. So, what if someone asks you to do this? Of course you can. You just got to do it like we did last lesson. You'd have to evaluate this directly. We won't do it now, but we have to evaluate the problem directly. Right? Did they give a path? No, it wouldn't hurt to do it right now. Let's do that. And it only takes a second for us to evaluate this. We're going to evaluate this directly. So can I do this? No.
No.
That's not going to work this time. So I got to do this directly because this vector field is not what? It's not conservative. Can I write this? Look, can I do this? No, you can't. It doesn't exist. The function doesn't exist. So, what's the path we got? We're just going to do this directly. That means I'm going to do this. F composed of RT dot R prime of T. Alright, what's the path they want us to take? And when I'm doing number 2 from these practice problems, they want you to go from 0, 0, 0, what's the other one? 3, 4, 5, and they wrote the word, you got to go along a line segment. Aha. That's a challenge in itself. We got to remember how to parameterize a line. How do you parameterize a line? Let's go with, and when this is the path, they didn't give it to us. I am now parameterizing a line. There's my x, there's my y, there's my z. This is the RT. So 0, 0, 0, and a plus, and a plus, and a plus. What goes in front of these t's? Right in front of all those t's is the parallel vector. To get the parallel vector, we do tip minus tail. What's 3 minus 0? 3. What's 4 minus 0? 4. And what's 5 minus 0? Ah, this problem isn't so bad directly. But others can be really nasty, you follow me? That's why they can now work this problem out. Well, it's not too bad. There's R of t. Now be careful what goes here. Not R of t, but what?
R prime.
R prime of t. Ah, I've got enough room right here to write R prime of t. A little bit of dt. I've got enough room to do f of r. Now what's R prime of t?
3, 4.
3, 4, and this problem is not bad directly, but I'm doing it directly. I'm not doing the what? I can't use this, so I'm just going back to the math method. Okay, but it was an easy vector field. We see that. The more complicated the vector field, the more complicated this is, the more complicated the path. What's F composed of? R of t. Ah. I think I've got enough room, don't I? Yeah. Negative y. That means negative 14. X is 3t. And what's this? Oh, just the z component, which is 5. Now, the big question. What's the limits? Always happens with a line. 0 to 1. This always happens with the line, because we did tip minus tail, right? Tip minus tail, this is t equal to 0. This is t equal to 1. You can check it. Plug in 0, plug in 1, you'll see you get that. So my limits are 0 to 1. What's that dot product? This problem not hard to work. What's that times that?
Negative 12t.
Alright, so you got to do the integral from 0 to 1, negative 12t plus
60, 12t.
12t, good, plus 20t. Oh no,
25.
25t dt. Any suggestions how to work that integral?
This 25t.
Knock these out. What's the integral of 25t?
25
Well,
over
t
2.
squared over 2, plug a 0 and a 1 in there. What's the work? The work done by the vector field to move a particle along that path would be 25 over 2. Sometimes working it out directly is not so bad, but other times it could be almost just absolutely absurd and ridiculous. So this comes in handy sometimes, doesn't it? But we couldn't use it there. Awesome. Now, we'll move on to this. This is rock. Oh, before I do green, there's one problem I need to show you. It gets people in tests. What about when they give you a table? So I'm going to write this out. Do you have this table here? I can actually pull up there. Is that number 6? Okay, I'll write it out. There's not much time, not much work to put this together. I was going to put on the overhead, but this table's small. This is x, and this is y, and we have a table here. The values are, I'm doing number 6, 0, 1, and 2. Okay, and these are the x values. 0, 1, and 2. And they give a table of all the x and y coordinates. This is 1, this is 5. That's 19. 2, 8, 25, and 3, 13, 32. Okay. And when they want you to evaluate del f dot dr. Here's C. The curve C is R2 equal to t squared plus 1 t. And you got to go from 1 to 0. They want to evaluate this. They write down an f as a function with a continuous gradient and with values f of x, y given in the table. So and here's the function of x and y values. But you'll notice they did write, hey, it's a differential function whose gradient vector is continuous. That accounts for it, because we just see a bunch of numbers in the table. Okay. There's the function values. What's the fundamental theorem alignment rule say? I'm going to work this problem, everyone. This equals it. This equals f of endpoint minus f of initial point. True? Oh. Well, what can happen during a test? What's the endpoint? What's the initial point? How do I find it? Look at all these numbers. Am I going to guess? Is that the endpoint? Is that the initial point? Is that the endpoint? Is that it? How do I find this? And it's something about this path given.